Good morning, ladies and gentlemen. Good morning. Hi, my name is Xavier Paradin, and I'm proud to be presenting on behalf of Team SeaSearcher, and we are presenting a better solution for data collection in coastal environments. Presenting with me today will be Thomas Macchio, Alex Andalia, Jay Fletcher, Eric Casada, and Nikhil Chari. So, SeaSearcher focuses on coral reefs, and the key takeaway from coral reefs is, of course, their biodiversity. The coral reefs worldwide encompass in their surface area 1/4 of the entire world's fish species. Now, attached to that biodiversity is a dollar figure. A composite of 80 valuations found that coral reefs were worth up to $172 billion annually. Now, most of this comes from tourism, but there are also some benefits from water treatment as well as pharmaceutical research and along those lines. Now, unfortunately, this very valuable resource is under threat. To take a specific example, the Great Barrier Reef of Australia, the largest reef in the world, composed of over 2,900 individual reefs, lost in the 30 years prior to 2012 over 50% of its initial area coverage. So, this project was brought to us by Dr. John McManus, and reaching out to more researchers in his field, including Dr. Kurt Storlazi, we looked into how they look into coral reefs and how we might propose a project that would be of use. So what you're seeing here is a video of a transect. It's where a researcher is being towed behind a boat in a straight line across a coral reef, collecting data such as video, temperature, and depth. And when communicating further with our researchers, we identified these particular needs. They want to do environmental impact studies, assess proper growth conditions for coral reefs, and increase the awareness about coral reefs. And this would require imaging, temperature, and depth data. Furthermore, Dr. John McManus specified that he would like an autonomous system to make mapping shallow reefs particularly effective. And with that, I would like to pass it on to Thomas to go over our objectives.
So we set a bunch of project goals at the beginning of last semester that we'd like to accomplish. The first of which had to do with portability. We originally wanted to keep our product under 20 kilograms and have it comply with FAA regulations because our ideal consumer will work alone and have to travel to remote locations to collect their data. Additionally, we wanted to be able to snap clear photos of the environments we were surveying, and therefore wanted to install both frontward and downward facing HD cameras. Our depth data range we set at 0.5 meters to 10 meters because that was dictated by the coral environments that we wished to survey. In terms of control, we wanted to have both remote control and autonomous waypoint guidance. And finally, for endurance and cost, we set our minimum battery life to be about 6 hours and our maximum cost to be no more than $3,000. Here's a plot of cost versus coastal suitability, or in other words, the ability of a product to meet the project goals as mentioned previously. We use this plot to compare existing solutions to our proposed solution. So on the top right is one existing solution as mentioned previously by Xavier. It's known as a tow board, and as you can see, this is a researcher using it, and it is particularly suitable for coastal environments because it is effective in collecting data. However, the continuous costs and the high effort level is the reason that it is so high up on the y-axis. On the top left is a device, known as Wave Glider, and this is on the order, or it costs on the order of about $300,000. And is not particularly suitable for coast because it is designed for deep sea environments. On the bottom left is a device known as SimpleScan. And SimpleScan, while relatively inexpensive compared to the other two products, is not doesn't particularly perform well in coastal environments because it doesn't have the sensor package necessary and also does not have the stability necessary. This bottom right green square is where the ideal product would lie on this plot. It would be maximized for coastal suitability and also would not cost much to produce. Overlaid on top of this plot are the ideas generated at the beginning of the semester to tackle this problem. We thought of everything from seaplanes to monohulls to catamarans, and we decided to move forward with the catamaran design because of its ability to be stable in these coastal environments and also the ability to produce at such a low cost. And on the bottom right, you can see our final product design known as the SeaSearcher. With that, I'll handle it over to Alex to discuss system design.
Thank you, Thomas. So I'm going to be talking to you guys about the final prototype design of SeaSearcher. Now, you'll see here, there's a photo of our fall prototype. It's clunky, it's heavy, But more importantly, we learned that in that central little waterproof box there, it's just a mess of wires. And we couldn't have that. We had to simplify it so that we could add more advanced sensors. Now here's our central enclosure. It holds almost all of our electronic systems. You can see the GoPros going in. Now we chose GoPros because they're small, they're easy to use, they have a great field of view and high definition. Next is our laser package. That's used for video scaling with the images taken from the GoPros. Next is our custom circuit board. This was the main reason why we were able to get rid of all of those wires, have everything that we needed to be housed in this small enclosure in the center, and as well as achieve our waterproofing that we needed with those connectors. Next is a P39 triducer. It measures depth, temperature, and speed and is attached to the rear of the enclosure. What you see here is the aluminum tubings being attached to the central enclosure. This is how we attach the middle sensor package to the pontoons. This allows us to telescopically change the width of the boat. Next, you can see our waterproofing system. It's an outer lid that presses on an inner lid into an O-ring to make sure that it's completely submergible. Next, those are our antennas and navigation light for GPS and for our wireless communication. Next, the T100 Blue Robotics thruster is our propulsion system for this vessel. It gets attached to the pontoon like so. As you can see here, our pontoon was created by using both a positive and negative mold to get that cavity that we so needed. We poured in a urethane foam mix to expand to make sure we had that exact shape. Inside that cavity goes our custom battery pack. It has 24 cells, it outputs 300 watt hours, and it puts it out at 12 volts. Next, this whole pontoon, as well as the central closure, are fully submersible. We were able to do this by using a lid system as well as IP68 waterproof connectors and waterproof on-off switch. Here is how we connect our pontoon to our central enclosure via the telescoping aluminum rods, bars. Here is the overall system design. You can see how it is all connected. We have our wiring, which is so much more simple than our initial fall prototype. Everything is compact. It has overall specs of a weight of 19.9 pounds and a range of 20 kilometers. So, portability. Furthermore, it's important that we were able to change the width of our pontoon using our overall device using the telescoping ability. It fits into a check-in luggage that allows for easy movement on any mode of transportation to any testing site. Next, as in any vessel of any size, stability is extremely important. This graph here shows our riding moment versus heel angle of the SeaSearcher. Furthermore, we calculated the metacentric height based off of our design. And we're happy to inform you, my bad. The metacentric height is the initial stability measurement. And we're happy to inform you that the SeaSearcher final prototype can be deployed at 89 degrees and it will still ride itself. Next, I'm going to hand it off to Jay, who will talk about our custom electronics.
Thanks, Alex. So Alex was mentioning the circuit boards provide a way to really simplify the wiring in the center of the boat, and we have a lot of different components that all fit into this very small area. So circuit boards include buck converters for improved efficiency for powering the boat, and also the GoPros so they don't die taking video. And they also have Wi-Fi modules to control the GoPros, an IMU for navigation purposes, and a XB for wireless communications. They have a 32-bit ARM microcontroller that controls everything and communicates back to the computer. And it also has a GPS module that allows you to get accurate positioning. And making a custom circuit board also allowed us to customize some things, such as putting an extra filter on the GPS signal to get more accurate positioning, and also adding an extra backup battery so that it can fix onto satellites much more quickly, so you don't have to wait for a while before you can start using the SeaSearcher. We also designed a nice user interface to make it easy for the user to control the boat. So they just have to connect the base station, which I have here, and they just connect it to their laptop with a USB cable, and they can immediately connect and start sending data to it. You can easily click to place waypoints, and the system designs so that it's easy to use even if you don't have a lot of technical skills. And you can save and load the waypoints so you can do this in advance or rerun trials you've done in the past to see how the corals changed over time. And you just have to click the start button and it'll start following the path. And now I'm going to hand it off to Eric to talk about the dynamics and controls of the system.
Thank you. So in order to autonomously control our boat, we had to develop a dynamic model of the system. We did this by deriving equations of motion for each of our 3 degrees of freedom. Here, in our forward direction, we have our 2 inputs, or our thrusters. We also have a drag component and a force external vector that captures things like wave action and underwater currents. In our side direction, we don't have any inputs, but once again, we face drag and that external force vector that has waves and currents. Our last degree of freedom is our yaw direction, or our heading angle. Here, once again, we can use our thrusters to control this, and we again face an additional drag component. With these equation of motions, we utilize MATLAB to create a virtual environment where we can test our autonomous control. This is one of those controllers. You can see it following a series of pre-described waypoints. On the top right, you see the response of the controller, and on the bottom right, you can see the thrusters reacting in order to make turns. With this successful model, we move to real-life trials. Here you see our boat in a lake in New Jersey. Here we're testing radio control. The reason radio control is important is in case of emergency, and it also gives the researchers flexibility in how to perform their missions. How we achieve radio control is through an iPhone app that allowed us to tilt to control the boat. Here you see data from our first real-life autonomous run in black. Overlaid is our MATLAB model of how the boat should behave in red. The waypoints are described by the plus signs, and the area around the waypoints are thresholds for how close we need to hit to those waypoints. As you can see, the model and the real-life performance is closely related. This allowed us to reduce the amount of trial and error in tuning our system. Here you see a system-level overview of one of those autonomous runs. You'll see the boat change direction to face the waypoint. On the bottom left, you see GPS data overlaid on Google Maps, and on the bottom right, you see what the bottom-facing camera is looking at. And you can see Alex move the phone to prove it's autonomous. And with that, I'll hand it off to Nikhil to talk about further validation.
Thank you, Eric. So in order to make sure that our system was as good as it can be, we decided to fly to Florida last weekend to test with our stakeholder and in the operating conditions. So here's a video of our boat testing in the actual environment that it will actually be testing in. And so you can see that it is very stable in the waves and has consistent stability and movement, which is always good to see. Here's a video of the front-facing camera showing the coral reef that we were studying. This is actually a fossilized coral reef, and you can see that the images and video is not blurred, and it's really good for scientists for that purpose. Here is an image mosaic taken from the bottom-facing camera. And so this is actually what scientists like Dr. McManus will be able to study, and 5 years later come back and take another study and compare the changes in the coral reefs, which will really be good for analysis purposes. And here's a photo of us with our stakeholder, Dr. McManus, in Miami. He was really, really pleased with our system stability, consistent movement, and portability, and controls. And so really would like something like this after senior design. We were actually able to hit most of the metrics that we desired, actually being under the weight by about half, which allows for future potential sensor packaging and other possible ways to deploy SeaSearcher. We are able to take clear photos with our bottom and front-facing cameras, and we're able to have autonomous remote control and waypoint-guided control. Unfortunately, our depth sensor en route to Miami stopped working, and so we're looking at ways to sort of fix that and try to debug it. However, we're potentially able to calibrate the depth using different lasers that we have aboard. In addition, our theoretical endurance time is actually 7 hours instead of the 6 that was desired, and we are potentially able to manufacture this at a cost of around less than $3,000 if we manufacture 100. With that, I'd like to thank our advisors, Dr. Mark Yim, Dr. Graham Wabushevsky, and our lovely TA, Mr. Sam Guardsmo, as well as the other host advisors that have really helped us through this process. And I'd like to thank Penn Engineering and the Berkman Fund. With that, we'll take any questions.
What was that? So the specific researcher we worked with works very much internationally, and right now he's working in the South China Sea, which is very military-based. There's a bunch of countries there, so he doesn't receive a lot of funding to work there because it's dangerous and controversial. But mostly, a lot of the systems that we looked at are also like plus $10,000, so we just try to make it as cheap as possible. Yes.
Often, what percent of the time do you say the conditions are suitable for this device? It seems like it's really susceptible to wind and things like that.
So because this is supposed to be deployed by a researcher, we expect him to show kind of awareness of those conditions and not deploy it if it's too choppy. Choppiness also creates sediment in the water, which reduces video quality and makes most of the results not usable. So it's up to them, really. conditions. So if you go to reef conditions, so wave height is a statistical thing, and we calculated the 1 in a million wave will be about 2 meters. But again, it's up to the researcher to show his ability to gauge conditions when deploying the craft.
And also, the tipping angle is almost 90 degrees, which makes it hard for it to tip over unless you had a really big wave.
We'll take one more question.
Yes, I'm curious why you chose a floating device instead of submersible, where you have issues of water clarity, surface conditions.
Because reefs are these environments with a lot of like branching structures, a submersible would require object avoidance, and it'd be just a lot harder to control. And the reefs that specifically John McManus studies are called fringing reefs, and they're very shallow. They're often above the water during low tide. Unfortunately, we'll have to call it there. We can speak afterwards. Thank you.
Awesome. You answered all the questions.